icon that they are, it's no surprise that to this day, thousands of rubber duckies are being constantly shipped all over the world, bringing joy to thousands of bathers every day. However, not all on their courageous journey make it to their final destination. On the night of January 10, 1992, a 98,000-ton container ship called the Everlaurel was headed from Hong Kong to Tacoma, Washington. While in the middle of the Pacific Ocean, passing through the international date line, the Everlaurel, along with all its crew and cargo, found itself right in the center of a nasty storm. While being thrashed back and forth in the waves, the Everlaurel lost 12 40-foot containers into the sea. Among those 12 containers, one of them somehow burst open, releasing its contents into the raging Pacific. The container, owned by a company called The First Years Incorporated, contained approximately 28,000 rubber ducky-based toys, including red beavers, green frogs, blue turtles, and of course, the original yellow rubber duck. The toys were released into the world, drifting endlessly into the open waters of the Pacific, never to be seen again. Or were they? James Ingram and Curtis Ebermeyer, two oceanographers taking on a rather ambitious goal, that goal being trying to create a map of the Earth's surface currents. Normally, their method for collecting data consisted of releasing between 500 to 1,000 of what are called drift bottles. These were essentially pirate-style messages in a glass bottle, with the words "break me" able to be seen on the paper through the glass. The flyer inside contained instructions on what to do after finding one, as well as informing the finder on the nature of the study, even sometimes offering a financial reward for finding the bottles. However, only about 2% of the bottles released ever made it back, making gathering significant data for the study seem impossible. But after hearing about the Everlaurel incident, Ingram and Ebbesmeyer kept a keen eye out, knowing that eventually the ducks would make their return. On November 16, 1992, approximately 10 months after the ducks were initially released, a local beachcomber in Sitka, Alaska, found 10 toys that were confirmed to be a part of the spill, nearly 2,000 miles from where they had originally started. After getting word of this, the pair contacted the locals and beach workers and managed to locate hundreds more of them along a 530-mile shoreline. Between November 28th of that same year to August of 1993, 400 of the ducks were discovered along the eastern coast of the Gulf of Alaska. After logging this information into a simulation of surface currents that uses information of air pressure starting from 1967, Ingram was able to use the data to accurately predict where many of the remaining toys would show up. Using their simulation, Ingram and Ebbesmeyer developed a model that led them to conclude that most of the floaties will travel the following route. First, to Alaska. Then west to Japan, back to Alaska, and finally drifting north through the Bering Strait, only to become trapped in the Arctic ice. Ebbesmeyer and Ingram predicted that it would take about 6 years before the toys would be thawed out and continue their journey. This story gained so much traction that in 2003, the First Year Incorporated actually offered a $100 savings bond to anyone who could recover any floaties in Iceland, New England, or Canada. More and more of these toys are turning up every year. However, these days, due to exposure to the sun, the ducks and beavers have faded to white. But with every toy that turns up, it has taught us more about how our ocean's currents work than any study has before, leading to what is most likely the greatest accidental study ever created.
Have you heard that heat rises? Well, here you can see it's true for yourself. I've got some food coloring on the bottom of a plastic container, and there's a hot mug right underneath the red food coloring. As it's heated, the water rises. But I want you to look closely and notice something else. The blue on the sides is being drawn in. You can see it better when I speed it up. Here's the thing I want you to remember. When water moves from one place, it doesn't leave a void behind. Water from somewhere else has to move in to take its place. That's why you can see the blue food coloring coming in from the sides. You can see it better from above. Watch that blue food coloring get drawn in. Do you see it? The hot water reaches the top, and then it gets pushed toward the edges by more hot water rising from underneath it. As it goes out to the edges, it starts to get cool, and cool water sinks just as hot water rises. And if you watch really carefully, you can see it sink and get drawn back toward the middle. These are called convection currents, and you see them moving here in two big ovals. They're one of the major things that drive ocean currents, especially in the deep oceans. But it's not hot water rising that drives the ocean currents. It's really cold water sinking up near the poles. Here's a piece of ice that I froze with some blue food coloring in it, so you can see how cold water sinks. As water sinks at the North Pole, for example, water has to flow up from southern regions to take its place. And these currents travel around the globe.
I don't think it was just an up and down movement that made it hard for me to stand up in the waves. There was definitely a push. Wasn't that the waves too?
Nope. The push is the current. A current is the constant movement of water in a river or ocean.
So the waves and currents work together. No wonder I couldn't stand. It was 2 against 1.
Yeah, currents are pretty powerful too. And unlike waves that just go up and down, a current moves in giant circles.
Currents sound kind of tricky.
Well, they can be. There are actually 2 different types of currents: surface currents and deep water currents. What you felt was a surface current. Surface currents move along the edges of continents.
Where'd that surface current get such a powerful push?
Surface currents are pushed along by the wind and the Coriolis effect.
And you lost me. Coreo what?
The Coriolis effect. It's the effect of the Earth's rotation that causes wind to move in a curved path, east to west instead of north and south. Because the wind's direction is controlled by the Coriolis effect, the direction of the currents is too.
Okay, that makes complete sense. Anything else I should know about surface currents?
One more thing. Surface currents affect weather and climate. As they move along the edge of the continents, they bring hot or cold water along with them. Winds blow the warm or cold temperatures carried by the currents over the land and cause changes in the weather and climate along the coast.
What about deep water currents? The wind can't do much for them if they're deep underwater.
You're right. Unlike surface currents, deep water currents are moved by temperature and saltiness, not wind.
Yeesh. Between the waves and the currents, there sure is a lot of commotion in the ocean.